Inductive reasoning, the number trick. So you've tried 4. I'm going to try 4. Pick an integer. How about 0? Add to this the next 4. So that'll be 0 plus 1 plus 2 plus 3 plus 4, which is 10. Divide the total by 5, which is 2. Subtract 2 from the answer, and you get 0. Okay, how about 5? So that'll be 5 plus 6 plus 7 plus 8 plus 9 is 11, 18, 26, 35. Divide the total by 5. 35 divided by 5 is 7. Subtract 2. You're back to 5. Let's try negative. So negative 10. So it'll be negative 10 plus negative 9. Now we've got to count our way up, right? Consecutive numbers are going up. Plus negative 8 plus negative 7 plus negative 6. 1, 2, 3, 4, 5. So that's 13, 21, 30, 40. That's negative 40. Divide by 5, you get negative 8. And subtract 2, you get negative 10. And let's just do 10. So 10 plus 11 plus 12 plus 13 plus 14. So that's 21, 23, 33, 36, 46, 50, 60. Oops, that's 60. Divide by 5, we get 12. Subtract 2, you get 10. What conclusion can you make? You're going to end up with the number you started with. So I end up with the number I chose, the integer I picked. Okay, so if we went around the entire class, we could probably find that we had a total of maybe 30 or 40 different numbers, right? And it worked for those. And then there's Sam, tried this trick with 15 different numbers, and each time he did it, he always got his original number. Even though Sam did not try it for all numbers, based on this research, he generalized specific examples to all numbers and made the following conjecture. If you do this number trick on any integer, you will always get your original number. Okay? And that's called inductive reasoning. Okay? The definition of inductive reasoning is going from the specific to the general, right? I did some specific examples, and I think that in general that's true. Now, a conjecture is a statement that you believe to be true, although you have not yet proved it, right? So Sam thinks that it's true, and we kind of agree with him because we've tried it with a bunch of different numbers. We think that it's true that if you do that number trick, you're going to end up with your original number. This is an example of inductive reasoning. Okay, and inductive reasoning goes from general conclusion. Okay, this is an example of inductive reasoning. Which involves drawing a general conclusion from several known cases. Okay, so we try something a few times, right? And we say, hey, I think this is going to be true all the time. Okay. Inductive reasoning is the process that begins with examining particular patterns and then drawing a general conjecture based on those patterns. Okay, so you're going to come up with a conjecture, right? This is how all of science works pretty much, right? You observe something, and then you come up with a conjecture. They call that the hypothesis. Then you try and prove that. Okay, so is this true all the time, right? I've seen it in a number of cases. Is it always true? Okay, so we work from the specific. I tried it for 1, I tried it for 2, I tried it for -5, I tried it, so I tried it for what? 0, 10, -10, 5, and it worked for all of those. I've done a positive number, I've done a negative number, I've done 0. It's worked for all of those. I think it's going to work for them. Okay. Have I proved it? No. I have not done a general proof. Okay, and that's really what deductive reasoning is, but that's a day or two away. Well, that's a day away, it's tomorrow. So that's deductive reasoning would be, okay, we think it's true, now let's prove that it's always true. There's nothing more there. Prime numbers. Mathematicians have been trying to determine an expression that will always generate a prime number answer when a natural number is substituted in the expression. Sam came up with the expression n squared plus n plus 17. Test to see if this expression generates prime numbers by evaluating the expression for the following numbers. Okay, so we want to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The first three are doing for you. I'm going to show you an easy way to do this. We can use our calculator, right? So get your calculator out. Let's learn a calculator trick. Just got to scooch that up a bit. Okay, calculator trick. Go to y equals. We're going to put in the expression n squared, only it's going to be x. So x squared plus x plus 17. Okay? And then we just go into the table. So when x is 0, we don't want x is 0, right? But when x is 1, we get 19, 2, we get 23, 3, we get 29, 4, we get 37, 5, we got 47, 6, what else we got? 6, 7, 8, 9, 10, 11. So 59, 73, 89. I can remember 3 at a time. 107, 127, 149. Okay, so that's a little faster way of doing it than, you know, if we sat down and calculated each one separately, right? Did you always end up with a prime number? Okay, what's a prime number? What's the definition of a prime number? Yeah, the only factors are 1 and itself. Okay, is 1 a prime number? Yeah. No, it's, yeah, right, it's a special number. 1 is special, it's not prime. So that's by definition, right? Because 1 is divisible only by itself and 1, but 1 is not a prime number. So the first prime number is 2. And 2 does a really neat thing with prime numbers. It takes out every other even number, right? Because every even number is divisible by 2. So the only even number that's prime is 2. But we want to check these guys now. Did we always end up? So is 19 a prime? 23. 29. 37. 47. 59. 73. 89. Anyway, think about it. So 89 might be divisible by 3, right? So does 3 go into 89? No. Okay. 107. 127. 149. Well, wait a sec. What's 149 divided by 3?
7.
It doesn't work.
Doesn't work? Okay. What's 149 divided by 7? No, that's not going to work. All right, so we're going to say, yeah, looks like we always. You should have seen the expression did work for the first 11 numbers. Complete the following conjecture. All right, so we have 11 things saying, yeah, this works, right? So when any natural number substitute the expression n squared plus n plus 17, then what do we get? We will get a prime number, right? So when any number, then the result is a prime number. Here. And the result is a prime number. So do you think this is always true? Okay, you got 11 examples. Seems reasonably convincing. 11 of them, it seems to work. What kind of reasoning did we use? Read the words from the top of the page. Inductive reasoning, right? We have specific cases. Okay, we got this expression. We put in 11 numbers. It worked for all of them. That's inductive reasoning. We've come up with a conjecture, which is that, yeah, this works. It's going to be prime. Okay, so do you believe it's true? Yes. It turns out, however, that this conjecture is false. You know that it's false because I said it turns out, however. Right? I mean, hey, it looked good. We tried 11 numbers. To prove any conjecture is false, you only need to provide, what do we need to provide? What's it called?
One example that doesn't work.
One example that doesn't work. A special name for an example that doesn't work. What's it called?
An example that doesn't work.
An example that doesn't work, but there's a one-word word for an example that doesn't work. You have one of them in your kitchen, near the sink.
Sink.
No. Here's the sink and here's the counter. It's a counter example. So you need to provide one counter example. Okay. So a counter example is just one example where it doesn't work. Look, we tried it with this number and it doesn't work. Then it's not true, right? The conjecture is not true. So no matter how many examples you have, but it worked for all of these numbers, yeah, but it doesn't work for this number, so it's not true.
So what's that number that doesn't work?
We'll get to that in a second.
Okay.
No, maybe we won't. Or is it down here? Do you have it on your sheet? Oh, okay. So what's it say? Okay, so a counterexam doesn't work. So here's what it says. A counterexample. Yes.
You're not recording.
Am I not?
Mr. Yanniver, a student is trying to tell you that you're not recording.
I get that. That's why I paused and said, am I not? And yet, it is still recording, so it's okay. It's all right, kids. It's still recording. Don't panic. It just got hidden when I moved it around a bit so I could pull the calculator out. So counterexample is this. N is 17. Try it. Try N is 17. All right, turn this back on. Let's go down to 17. Go down. Go down. 323.
Divisible by.
I bet you it's divisible by, wait for it, 17.
It is.
Yeah.
19.
Okay, so why? Think about it. We had n squared plus n plus 17, right? So if we use 17, that's a multiple of 17. And then to that, we're going to add 17. And then to that, we're going to add 17, right? So this is 17 times 17. That's 17 17s. This makes 18 of them. This makes 19 of them. So we end up with 17 times 19, and that's not prime. Okay, so is the conjecture true? We thought so, but no, we found a counterexample, right? That's all we need, one counterexample. Okay, so this was 17 squared plus 17 plus 17, right? So that's 17 of them, 18, 19, 17, right, was 343.
323.
323? 323, right? 3, 2, 3. Pythagorean triples.
Whoa.
Show the numbers 3, 4, and 5 satisfy the Pythagorean theorem. Three natural numbers that satisfy the Pythagorean theorem are called a Pythagorean triple. Okay, so what do we do with 3, 4, and 5? What is the Pythagorean theorem? Give me a statement.
A squared plus b squared plus c squared.
Okay, so a squared plus b squared equals c squared, right? It looks like this. I got a 90-degree triangle, and there's a, b, and c C is the hypotenuse, right? So it says the sum of the squares of the two legs of the triangle will be equal to the square of the hypotenuse. So that means we want to say, is 3 squared plus 4 squared equal to 5 squared? So 9 plus 16 equals 25, and 25 equals 25, and that's true, right? We put a little question mark over these, right? Say, we're checking. I'm just checking to see, is 3 squared plus 4 squared equal to 5 squared? So the little question mark over the equal said, well, is it equal? And then we're saying, well, is it equal? And then we're saying, yeah, it is equal. Okay, so that's a Pythagorean triple, 3, 4, 5. Multiply 3, 4, 5 by the number 2 and show that the new set of numbers is Pythagorean triple. So we multiply by 2, what are we going to get?
6,
6, 8, 10. Right? That's not minus signs, that's just a dash, right? 6, 8, 10. It's that set of numbers. Okay, is this also? So 6 squared plus 8 squared equals 10 squared. I'm going to throw a question mark up, right? I don't know. That's what we're checking. So this is 36 plus 64. Is that equal to 100? And 100 equals 100. Check. Okay. That's kind of an alternate method of checking, right? On the radicals, we did the left side, right side, the t-table. That's a much more formal way to check. Repeat the process by multiplying 3, 4, 5 by the numbers 3 and 4 and showing the new set of numbers are also Pythagorean triples. Okay, so I'm going to pause this. Okay, so it worked for 3, 4, 5 times 3 and 3, 4, 5 times 4. Do you think if you multiply by 5 or 6 or even k that you will get a Pythagorean triple?
Yes, because of the multiplication.
Yes. Okay, so we think we will. Write a conjecture based on your finding. Okay, so now you want to try and come up with, in your own words, how are you going to say this? Wait. How about this? Okay, so if we take the Pythagorean triple 3, 4, 5, multiply by any natural number, right? So natural numbers are like 1, 2, 3, 4, the counting numbers. Okay, you can't multiply it by 0. That wouldn't really work. Although 0 squared plus 0 squared is 0 squared, but sort of. Then the result will be a Pythagorean triple. So do you think that work with other Pythagorean triples, like not 3, 4, 5, but there's another Pythagorean triple which is like 5, 12, 13. Do you think that would work for that as well? Probably. Sure. Would you want to try a couple to see and then say, yeah, I think it does? Okay, so we might want to say, well, okay, for 3, 4, 5 it works, but if it's 5, 12, 13, will it work for 10, 24, and 26? Okay, well, I want to try that. Will it work for 15 and 36 and 39? I want to try that. I try a couple of them, I'm pretty sure, right? Because I know it worked for 3, 4, 5. I've seen 2 examples, right? And again, that's inductive reasoning, right? We see some examples, we make a conjecture, okay? So we tried it with 2, we tried it with 3 and 4. That's kind of enough for us to say, yeah, I think that works. Okay? When we get into deductive reasoning, we can actually prove that, yeah, it really does work for any number, right? Number patterns. Complete the following calculations. 1/2 minus 1/3. What do we need to do when we're subtracting fractions? Common denominator. What is the common denominator for halves and thirds? 6. So how many sixths is 1/2? Okay, do you want to see how we get the sixths, or are you just okay with the 3/6?
I think we understand.
Okay, so 1/2, 3/6, and a third is how many sixths? 2/6. And the answer then would be equal to 1/6. Okay? So remember, we're looking for a pattern here. Right now, we say is, yeah, okay. Let's do a third minus a quarter. What's the common denominator for thirds and quarters? 12ths. How many 12ths is 1/3? How many 12ths is 1/4? What's 4/12 minus 3/12? 1/12. Okay, you're starting to see a pattern. Okay, if you're starting to see a pattern, just keep it in your head. Say, okay, I think maybe I see something going on here. Let's try another one. A quarter minus a fifth. What's the common denominator? 20. How many 20ths is 1/4? How many 20ths is 1/5? What's 5 20ths minus 4 20ths? What do you think the pattern is?
4 times 5.
1 over the common denominator. Okay. So let's try 5th minus a 6. What's common denominator? 30. How many 30ths is 1/5? How many 30ths is 1/6? And what's 6 30ths minus 5 30ths? Examine your results and use inductive reasoning. Okay, so inductive reasoning, we've done 4 specific examples to predict, not calculate, the results of the following. Okay, so just write down, this is what I think the answer is going to be. Okay. Don't calculate it, just write down, okay, it's whatever over whatever. So 1 over what? 42. And the other one is 1 over 56. Okay. Now calculate. Okay, so we came up with the prediction, now let's calculate. So this will be 7 over 42 minus 6 over 42 is equal to 1 over 42. So that checks, right? It's 1 over 42. And this will be 8 over 56 minus 7 over 56 is equal to 1 over 56. Write a conjecture. 1 over n minus what? So if you think, if I'm looking at 1/7 minus, how is this number related to this number? Okay, so 1 over n plus 1, right? The next bigger number. So we've got 1 over n, and then we've got 1 over the next bigger number, n plus 1. And what's that going to be equal to? Which is, you need an expression for it. N times n plus 1. Okay, that's conjecture, right? So if we throw 5 in there, it's 1 over 5 minus 1 over 6 is 1 over 5 times 6, or 1 over 30, right? So that conjecture, now if we backtrack a little and check some of our answers, yeah, that conjecture worked for my answers, right? It's like setting up a word problem. When you go to set up the word problem, you always want to say, okay, I've got an expression. Does that actually work with for real numbers in there? Is my revenue actually this much money? Okay. Is something moving at this speed? Sum of the interior angles of polynomial. A triangle, quadrilateral, and hexagon are shown on the smartboard. Not really. Okay, a triangle, a quadrilateral, a pentagon, and a hexagon are shown on the smartboard. Well, they are now. Each polygon could be divided into triangles, right? So all I gotta do is start drawing diagonals, and I can make triangles. The least number of triangles into which each polygon can be divided will help determine the sum of the interior angles. So a triangle has 3 sides that can be divided into one triangle, right? It's just there. And what are the sum of the angles in a triangle? We know this, 180. Okay, if I take the quadrilateral, really? Okay, so if we draw a diagonal, we can split the quadrilateral into 2 triangles. And what will be the sum of the angles in 2 triangles? 360, right? Or 180 times 2, right? Because there are now 2 triangles. Okay, I have a pentagon, 5 sides. So I can split that into how many triangles? 3 triangles. So how many degrees in 3 triangles?
180 times. Yeah.
180 times 3?
Yes, sir.
Which is 540, right? Might want to kind of work backwards from this and do this equals. Okay, hexagon. How many triangles? 4. And 4 triangles will give us 720 degrees, right? Come on, all of you skateboarders or skiers or snowboarders should know all of these. Should know all of these rotations, right? 180, 360, 540, 720. What's next? 900, 1080. Yeah. What's the most anybody's landed in a competition? 1440.
On a skateboard, maybe 1080.
1080 on a skateboard, right? So. Okay, so we have actually drawn 4 of these things. Now we've got a septagon. How many triangles do you think we can divide that into? 5. And an octagon? And a nonagon? Okay, so what do I hear? 900. What was the next one? 1080. And then 1260. Right? So you didn't know it, but you can actually multiply by 180. All you guys, right? You just didn't really recognize it that, oh, hey, yeah. Turns out I can multiply by 180. Use inductive reasoning to complete the rest of the table except for the last row. Okay, so we've done that. We've completed the rest of the table, right? Got all these different ones. Write a conjecture by completing the following statement. Which apparently, oh, there they are. There, 2 triangles, 3 triangles. Am I missing something? Oh wait, you do one. Okay, 3 triangles, 4 triangles. Write a conjecture by completing. So the sum of the interior angles of an n-sided polygon is, okay, so look back, 180 times, no, n is the number of triangles, right? Or sorry, no, we want n to be the number of sides. So n minus 2. 180, right? So it's an n-sided polygon and it has n sides. Use your theorem to determine the measure of the unknown angle. Okay, how many sides? 5. What will the sum of the interior angles be? So we have 5 sides. Sum of interior angles. So let's write down S is equal to 180 times n minus 2. So we have a formula now. Substitute into the formula, 180 degrees times 5 minus 2. So 180 degrees times 3. So we have 540 degrees.
Why did you change the variable?
No, S is the sum,
Oh, yeah.
and n is the number of sides. Now we also know, from here, we know that S is equal to 130 degrees plus 112 degrees plus 155 degrees plus 78 degrees plus x degrees. So now we say, but we know S, we know that the sum is 540 degrees, right? Because it is a 5-sided triangle. And what do we got? 130, that'll be 142, 242, 247, 297, 397, 405, 475 plus x. So what's x equal to? Well, if we add 5, we'll get to 480, and then 60 will get us to 540. So 65 degrees. Okay? So we have a theorem that we've come up with. We used inductive reasoning. We tried 4 of them, and then we just said, okay, let's just keep going along this path. It seems reasonable. And we used it to solve. A regular polygon is one where all sides have the same length and all angles have the same measure. What is the size of each interior angle of a regular octagon? What's an example of a real-life regular octagon? A stop sign. So you see them every day, right? Every day you're wandering about, you're going to see a stop sign. Okay? And that's a regular octagon. Okay, so let's back up. 3. And let's go fill this in. Say, if we have n sides, then how many triangles will we have? N minus 2. And the sum of the angles will be 180 times n minus 2. Okay, so this is an n-sided polygon. Okay, so for an n-sided polygon, there are n sides. That gives us n minus 2 triangles, gives us the sum of the interior angles being 180 times n minus 2. So, octagon, 8 sides. So S is equal to 180 times n minus 2, that's our formula. S is equal to 180 degrees times 8 minus 2, which is 180 degrees times 6, which is 480, 1080. Okay. So, what's the measure of each angle then? What do we have to do to get the measure of each angle? Divide by, how many angles are there? 8. Yeah. And what's that work out to? 135? Okay, so each interior angle, right, because the regular octagon, so all the sides are the same length and all the angles have the same measure. So each angle, so let's just say each angle, it's the sum of the angles divided by the number of sides, which is the same as the number of angles, right? Determine the measure of angle ABC. There's no B. There's a B. Drawing a B, otherwise you can't do ABC. So an angle ABC, which angle are we talking about? Give me the, which expression?
2x minus 2.
No. Which angle is ABC? Which of these?
It's x plus.
X plus 10, right? So ABC says you start here, you go here, and you go here. This is the only angle, right? So it's the middle letter, really, of this one. Okay, going from A to B to C. All right, so figure it out. Okay, we're back, and you will notice stuff has magically appeared, right? So we have a 6-sided figure. We use the formula, which is given to you on your formula sheet, to calculate the sum of the angles in the polygon. But we also know the sum of the angles is the sum of each of these guys, right? So we set this up. And substituting in, we know the sum of the angles is 720 degrees, and we have, so I'm just going to add up x's, 3x, 5x, 8x, 9x, 12x. Okay, 10 minus 15 is negative 5, plus 10 is positive 5, minus 25 is negative 20, negative 45, so it'll be minus 45. And so now what we want to solve is, to solve 12x minus 45 is equal to 720. So 12x is 765. We're going to add 45 to both sides. and x is equal to, we're going to divide by 12, so 12 goes into 72 6 times, and then 445, that'll be 3 times, it's 36, that leaves a 9, I'm going to look, 63.75. Sorry, that's x, and angle B, angle ABC, is equal to x plus 10 degrees, so that'll be 73.75 degrees. Okay, because we want to find angle ABC. Okay, so that's it. You know, it looks like a whole big bunch of stuff, but not really, right? It's just a concept of, I have a 6-sided figure that has the sum of the inner triangles being 720. I have an expression for the sum of those inner triangles, right? You can use your calculator, right? Adding x's, just go 1 plus 2 plus 2 plus 3 plus 1 plus 3. And when you're adding up the numbers, just 10 minus 15 plus 10 minus 25 minus 25. Hit enter. You got 12x minus 45. Solve that equation. Notice these are both degrees. I've now dropped the degree symbol and just say so that number is equal. And I've got x, and then I go back to degrees here, and make sure you've got a degree symbol, right? So we need units, right? If we need units, then we need units. Picture patterns. 3 figures are shown. Figure 1. How many small triangles do we have in figure 1? We have 1 triangle. We just have 1 triangle. Okay, in figure 2, we have 4 small triangles. In figure 3, we have 9. Yep. Okay, so what are we going to do to get figure 4? So you need to draw figure 4 and figure 5. So it looks like we're starting with a triangle, and then we put a base underneath it made up of triangles, right? In this case, 3, and then in this case, 1, 2, 3, 4, 5. So and then each of these guys. And then each of these guys. I need to extend the base out a bit. There. Not the world's greatest drawing, but it's continuing the pattern, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So all I'm doing is just taking each line that I've got, turning it into a triangle down here. Closing that off and then completing the edges. Okay, well, what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25. Okay, now question, did I even need to draw? So, because it just says predict them, right? So I kind of went ahead a bit. So predict. So is there a pattern in the numbers? Figure 1 is 1, figure 2 is 4, figure 3 is 9. You're just squaring the numbers, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Okay, so really I kind of went ahead, right? 16 and 25. Is there a pattern in the numbers? Yes. Period. If yes, describe the pattern. Okay, I said yes, so the pattern is the total number of small triangles is the square the figure number. Using the pattern, write an expression for the total number of small triangles in figure n. What would figure n have? N squared. Right? Just square the figure number, right? So this is more general. This is a general case, right? So I say figure 9, you say 81. I say figure 12, you say 12 squared is, you figure that out, it's 144. Okay, I say figure 17, you gotta square 17. That's it. Okay. Now, wait, are we done? Yeah, we're kind of done.